Yeah, yeah. Thank you, Francisco, for the introducing. Yeah, it's right. I'm coming since 20 years here, and yeah, as you know, I really enjoy it a lot, and thank you again for the opportunity to speak here, and thank you that you're not becoming boring of my talk. So, and that's why today I decided to make more a little bit overview talk. Yeah. Uh, about things Francisco and me, we are doing together, also applications. I have to admit that this application to chip design, yes, it's true, but it's not like that we are building chips or something like this. Yeah? You will see. So maybe I start to explain what probably you know, algebraic differential equation is what you have. Yeah, normally you have abstract Cauchy problem, maybe with some inhomogeneity. Yeah. A is matrix or operator, yeah, and then you are interested in the eigenvalues of the operator, yeah? Or the matrix. And you know this all, yeah? And then so we continue. And DAE, differential algebraic equation, is if we have two matrices or two operators, yeah? And yeah, this is, I would say, it's very popular. There's a lot of research. There are many in control theory. There's something like what is called port Hamiltonian systems, or they make also differential algebraic port Hamiltonian systems. There are many research groups are working in this direction. Yeah? And well, if and now what is the before we had eigenvalue problem for if we have Cauchy problem, we look at A minus lambda identity, yeah, and the eigenvalues. What we have now, we have A minus lambda E, right? You could also say we make Laplace transform, and then we get the corresponding equation here. So this is the object I want to study today. Yeah? Also, in the case of matrices, but also for bounded operators. Yeah? And you can also do unbounded operators, which is also popular now. Okay. And then, so this is one storyline. And then if, of course, if E, the next point which will come later is the following. If, let's say, if E is invertible matrix operator, of course, you can put it on the other side, and you come back to standard Cauchy problem. And of course, this is, you can do, but this is boring, let's say. Yeah? Interesting is the case when both operators actually are singular. Yeah? So and then, but then using the, I will do it later, you can use some, so if the object, if E is invertible, then it's boring. So E has to be singular. And then, but we can also try to invert it. Yeah? And this is what Francisco and we are doing. So this the next part of the story is to consider this one and give this object a meaning. Yeah? And then study this spectral problem. And there are many ways, but there's one way which is connected with linear relations, subspaces. I will do it more in detail, where you always can give sense to this object. Yeah? There exists also more Penrose inverse and generalized inverse and pseudo inverse and so on. But this is the way we are some subspace point of view. You can always invert E. What you get is a multi-valued object. It can happen that 0 in some sense will be mapped to something which is not 0. And if you allow this, you obtain many problems, of course, but you can work with this object. Yeah? Okay, this is some general overview of the yeah, and then because it's an overview talk, I took something from many papers, so that's why there are so many collaborators. This is I already said I want to study this object SE minus A pencils, which could be matrix pencil or operator pencil. Yeah? And talk is divided into two parts. And I will start with matrix pencils. And here I will show, yeah, one can say the following. I will show here application standard from electrical circuits with not so much results. And here we have more mathematical results. Yeah? But not so many applications. So it's always okay. Yeah, this is the content. Maybe I don't. In part one, we want to move eigenvalues. In part two, we want to do something with the so-called essential spectrum. Yeah, and we have some applications for these two parts. But I will go into detail with part one. Yeah? Because this, so actually what we did, this was a with some colleagues from electrical engineering from my university, and actually we have in close by my university there was a center of East German chip design, chip industry, which was not the most successful one, but at least they have the technology, and out of this is one of the biggest chip producers in the world is located there. Nobody knows it. Everybody knows Intel and so on. And this is, I don't know, this number 5 in the world, or they have 8 factories. And we actually, the idea was, but we couldn't realize it, yeah, that this factory will produce the chip for us in the end of our research. Yeah? But we never ended. It was a problem. Yeah. Okay, this is the background why we became interested in these problems. Yeah? Okay, yeah, let us start chips. So this is, of course, some simple amplifier, yeah, and with the different with the different electrical elements to build. Yeah, so this is resistance. Yeah? And sorry, no, this is resistance. This is capacity, and so on and so on. Yeah? These are not interesting for us. There are some. I have it here. So let me see what. Yeah, current controlled current source. These are elements we use for chips. Yeah? These are okay. So each of these elements, which you all know, has the standard rules of how they behave. Yeah? The standard laws. Everything is, I haven't, it's not written down. Yeah, everything is time dependent. Yeah? So it's not set. And then when you make Laplace transform, sloppy speaking, yeah, the derivative turns into multiplication with the independent variable. Yeah? Okay, you get these rules, and then I don't want to go too much into detail. Yeah. What you do is it's called modal analysis. You look at various points, and then you let us take number 1, yeah, and then you see here is a voltage, yeah, and this is the resistance, and yeah, then you know that the sum of the current in such a model point is 0, huh? And you get such a matrix. Let us not, yeah. And here is some, yeah, here's some symmetry inside in this matrix, and the hope was that we can somehow use this properties, but it was not, we couldn't use. So I don't tell So now we look at this matrix here. Yeah? So and I want to write it in this form. Yeah, in this form. Now lambda is S. Yeah? And well, I colored. So yeah, here we are. Yeah, here all terms with S. Yeah? And all blue all terms without S. Yeah? And yeah, that's the form. And here you see, yeah, you see a little bit of the symmetry. Here and here, here and here, they have some, there's some structure. Okay. So this is how, yeah, in a very natural way, you get matrix pencils when you start to consider chips, yeah, or electric circuits. Yeah? And also because of the usually of the structure, it is very sure that they are not invertible. Yeah? Or very often they are not invertible. Okay. And okay, E and A, V and B. So we get this equation. Yeah? And now, I mean, this is nothing new. Yeah, this is very well known. And now we continue. And now we want to improve our circle. For this, let us solve for the first variable. Yeah? Usually you have yeah, you have some input and some out. I don't want to go too much into the system theoretic stuff. You have some input and some output. Yeah? And this you could think now, this is as your output. Yeah? This is what your system, what your circuit is giving to you. Yeah? And this can be solved in this. This is Cramer's rule to solve for the first for V1 is maybe, yeah, V1 was here. And yeah, and this this is sometimes also called transfer function. Or usually the engineers look at this transfer function. The transfer function describes, as I said, the answer of the system. And what you do is you look at the imaginary axis. This is electrical engineers use today. So you look at the imaginary axis, and this the behavior of this expression gives you what they call the answer of the system. Why? They put as let us state it like this. Yeah. So for the electrical engineering persons, this transfer function is, as I said, the answer of the system. The answer in the sense that you give as input some cosine expressions. Yeah. And then you see how the system answers. Yeah? And this is done via the transfer function. So, and the question, now comes the question. One would like to change the transfer function by adding a new capacitance. What does it mean, a new capacitance? Maybe I go back. Yeah, a new capacitance will give me, here is my these C's, yeah, CBC, yeah. Let us look at this CBC. then we get four, yeah, this corresponds to 4 entries, yeah? CVC, 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 yeah? And a new capacitance put like I don't know, like here a new one, yeah? And then I get 4 new entries into my matrix. Yeah? So actually, what does it mean? I make a one-dimensional, and they are all in E. I make a one-dimensional perturbation of E. Yeah? And then I want to change the transfer function. Go back to transfer function. And transfer function is, you see, yeah, the main part is this determinant. And the determinant somehow is, yeah, of course, we were somehow simplifying. We were saying, okay, this expression we cannot really control. Yeah? Let us try to move the eigenvalue, so the zeros of this expression, somewhere, yeah? And hope that the transfer function behaves nice, yeah? Improves in some sense. And improving, I will show you what does it mean improving. So this is here it's now written more formally, yeah. So we change T by a one-dimensional perturbation because of the small symmetry we have in the matrix. You know that adding a capacitance will give you a P of this form. Yeah, this is of course unit vector, and the perturbation looks like this. I will not stress too much on this structure because we couldn't use the properties, or up so far we couldn't use. Okay, and yeah, this is again the same. Huh? So to repeat my, yeah, we add a capacity, and the engineers, this comes now from outside math, if you want, yeah? The engineers want that the eigenvalues are always on the left-hand side because the underlying system is stable, and but we want also to move them towards this blue area, because it is hoped that we move them. The idea is very simple. If the just heuristic, if the pole is close to the imaginary axis, then it will destroy the nice behavior of my transfer function because close by I have the pole. Yeah? So this is but ruled by some, let's say. It's not yeah. Here's some example. Miller operational amplifier. This is somehow, for us it's not so important what it means. This is one of the examples which is already big enough, so that you cannot do it by hand. And then there's some. In the end, the idea is to add maybe 5, or I don't know, 500 capacities, and then your chip or whatsoever behaves better. Yeah. So this is some example done by the engineers. They do this, or they did this without mathematics, just by trial and error. Of course, these network designers, they have a lot of experience. They know, of course, they know what happens. So yeah. Good. So what means good? What means that the transfer function has good properties? This is just a schematic picture. It's not proven. And so yeah, you see if the eigenvalues go just yeah, vertical up, then you get this happens. Yeah? So the transfer function gets some peak, let's say. And if they go to the left, transfer function goes down. And what they want to have is, that's why they want to put it on these two diagonals. This will create a long and stable answer. This is what they, yeah. It finally goes down, but they want a long answer for some. Okay. And I mean, this was our approach. Yeah. This was the real what you often do in mathematics, right? The real goal, you have no idea how to get it. Yeah. You take some substitution and hope that the substituted model is will give you some good result. This was the idea. Yeah. This we cannot no idea how to do this. Yeah. But maybe we can control. Yeah? So instead of solving this problem directly, we solve this eigenvalue space. No, yeah, we solved it a little bit. Good. So this is yeah, this is I think this is somehow a little bit of repetition again. So but why not? Yeah. So add such kind of perturbation to E, and then the zeros of the determinant we want to control, the eigenvalues we want to control, and we want to put them on the line. Okay. So now first thing, I said it already, actually in the application we are restricted to such perturbation, which corresponds to adding a capacity. But we can we couldn't work with this, so we had to relax the problem and allow study first any one-dimensional perturbation, and then somehow hope that we can approximate this one or whatsoever. Yeah? So instead of this perturbation, we look at this. Then let us start. Let us start with following question. We start with a pencil, and this pencil has a green eigenvalue. Yeah? And shall I say eigenvalue? I mean, it's clear, right? Lambda is, I haven't said. Lambda is, if I call this guy, oh no. Let me call this A of lambda actually. Okay. Mu is an eigenvalue of the matrix pencil. Yeah, if it only is. Yeah, as what you would expect. Yeah, there exists some V not zero such that A minus lambda E V is zero. Huh? It's eigenvalue for matrices. So again, we start with a given matrix pencil with green eigenvalues, and they are not, we don't like them, right? They are too close to the imaginary axis. And we want to shift them into the violet ones, into the mu. Yeah? And the mu's are in some area. Okay. And the question is, can we find one x such that here we have some, this is now the perturbed pencil. That's the spectrum of the perturbed pencil is violet. Yeah? And yeah, this we can characterize whether this is possible. Okay. And I will show you the result. The result, yeah, is a little bit technical. So for this, we need unfortunately the so-called, it is a good point to say, I haven't stressed it so far. These are E and A are Hermitian matrices in our situation. Yeah? So far it was not important. Yeah? And there is a well-known, very old result, normal form for Hermitian regular, maybe they have to satisfy some small property more that not the complex plane is full of spectrum. Let us not stress this point. We have some here we have some assumptions. This normal form for Hermitian exists is true for every Hermitian matrix pencils where E and A are Hermitian matrices. But I only use the special form here because in the application we have only this kind of simple and semi-simple eigenvalue. Yeah? And then the canonical form is simpler. Otherwise, the form is a little bit ugly. Yeah? So we assume, as I said, the normal form is valid for all pencils, matrix pencils, but we use only the special one where we have simple finite eigenvalues and simple eigenvalue at infinity. Yeah? You will see them. Otherwise, essentially, we don't have Jordan things. Yeah? So there exists what must be normal form, where I multiply my pencil with S and S star from the left and the right. Yeah? And then I get something like Jordan canonical form for Hermitian matrix pencils. And this canonical form is like the Jordan normal form consists out of blocks on the diagonal. And the blocks have the following form. I show you all. Yeah. So we have, so these are the real eigenvalues. Yeah. This goes for, and because I assume simple, it is only 1 times 1 block. Huh? Then we can, but this comes from the pencil theory. We have some signum in front, and this signum is very important. Huh? And this signum is expressed by -1 and 1. So it has either of this form or times -1. Then we have, so lambda, these are the complex eigenvalues, yeah? Also simple. And this, because it's a Hermitian pencil, they fulfill the symmetry condition. Yeah? Eigenvalue here becomes eigenvalue there. So that's why they are of this form. And again, simple. And here, this is the eigenvalue at infinity. It has also blocks, but it could, because I only assume simple, it could have several blocks corresponding to infinity. Okay. So this is and from this complicated normal form, I need this one and this one. Huh? That's why just for the epsilons, this is how I have some of you actually write Hermitian there's a relationship to prime spaces, right? This is you can associate the self-adjoint operator in a prime space to a pencil, and then this corresponds to the signs of the spectrum of the corresponding self-adjoint operator. So this is a relationship. Because some of you know prime spaces, so I can say this. Huh? Okay. And now comes our result, which is a little bit technical. Again, we need the same assumption. So, yeah, we assume here 0 with the spectrum of A, then it is regular, semi-simple infinity, simple eigenvalues. This was our, yeah, the ones we want to reach, the eigenvalues we want to reach. And then there, also they should be outside of the spectrum of the alpha operator. So this is technical. And then the result is the following. There exists such a one-dimensional perturbation satisfying with the desired spectrum, if and only if. And now comes something I don't want to, we don't go into detail, I suppose. What is it? We make here some products running over the spectrum and so on and so on. And then we have to, with these products, we have to fulfill time conditions. These pencils are very, these signs play a big role in this pencil theory. And the same here. We have two conditions. We have two conditions on the sign, and it's a little bit technical result. Okay. So in this sense, we solved the problem of the engineers, but we were cheating 2 times. First of all, we used this eigenvalue instead of the transfer function, right? And then this perturbation is not of the correct form. Plenty to do. Okay, part 2. Maybe I have to, Francisco, how much time I have? 1 hour in total, or less? I'm good in time. Okay. Yeah, part 2. Same story, yeah, but now we don't do it for matrices, we do it for operators. Yeah? And also, we focus more on the essential spectrum. Yeah, here we take 2 different Hilbert spaces, E and A. This means, bounded operators between 2 different. It's better actually to think of, let's say, X equals Z, but we can do it in this generality. And yeah, again, yeah. If you look back to this definition, this was not good that I took this one, but you can also say that, if you rewrite this, this means, so lambda is in the spectrum of A if we have this, okay? But this means that this operator, where we evaluate, what? Yeah, sorry. Yeah. So again, mu is in the spectrum of our pencil if it satisfies, if we have a V which satisfies this equation. And of course, but this equation means that V is an eigenvector at 0 of this matrix. So we can write mu is in the spectrum of the pencil if 0 is in the spectrum or point spectrum, let's say, of A minus mu E. It's just playing with these definitions, right? And but this now you can do with everything, We solvent set, essential spectrum, point spectrum, continuous spectrum, residual spectrum, always the same, And it plays no role whether it is matrices or operators. Unbounded operators is difficult, because then this expression is not has no sense in general. But we would, yeah, one can also, of course, one can do something. So, and in this sense, yeah, spectral, all these complex numbers such as 0 is in the spectrum of this object. And resolvent said, okay, it's a complement. Essential spectrum in. Yeah, I know I wrote it in a bit. Okay, yeah. So essential spectrum, yeah, all lambda such that this object is not spectrum. Yeah? Mu in the essential spectrum of my pencil, if and only if 0 is not in the pattern set, maybe we call it like this. No, 0. No, okay. Also, operator A minus lambda E. This means pattern set. Yeah? Okay. Also, I don't know how well known or how popular here spectrum operators. So yeah, just to recall, range, the code dimension of the range is finite, and the dimension of the kernel is finite. Yeah? We are bounded operator, and then if the code dimension is finite and the range is so yeah. Okay. And now the question is, yeah, it's more taken from, let's say, standard pattern theory, yeah, and you ask the question of the invariance of the essential spectrum. Yeah? Okay. Also, und well, I'm not aware of results for this. What is cheap, let's say, is of course if yeah. So yeah, not again. So invariance of the essential spectrum, which means I have two operators E and E hat, and two operators A and A hat. I form the corresponding pencil, and I look at the essential spectrum. I ask myself, please give me assumptions, conditions for E and E hat and A hat, such that the essential spectrum won't change. Yeah? And of course, one very easy thing is if the difference is complex. This stands for complex operator. Yeah, because then the difference of the pencils is compact, and if one pencil is not, if such a, again, same mistake, right? And if yeah, so if I check the corresponding A hat and E hat, right? If I compare these two objects, they have a complex difference. So when 0 is not in the pattern set of the 1, then 0 is and so on. Yeah? Nothing to prove. Okay. And we we, as I said before, in this sort of investigations, we now use the idea of linear relation. Yeah? So we look at the range of EA, which is this, and then we see the following. We can read it as a following. Yeah, what comes now is motivation why it makes sense to look at these objects. Yeah? So again, we look at the range of EA. Look this. This is yeah. And now we can read it as a column. Maybe I. So. So well, better to. So this is the goal. I want to see that this object corresponds to this. Yeah? Okay. So for this, first of all, so the idea is better. The idea is to understand how I can use it in terms of linear relations. And the idea is I want to write it as a product of two operators or two linear relations. Yeah? Maybe I have to motivate a little bit. I didn't want to put it on slides. That's why it's now a little bit. I think this should be fine. I don't. So, first of all, what is linear relation? As I said, this is just a subspace. So, let us say T. It's a subspace of X times X. Or I could also consider them between different spaces. Yeah? Thank you, Francisco. So, and so it's a collection of tuples. Yeah? And let us start with the standard. Why should one do this? Well, you know, we have in mind, yeah, we want to generalize the notion of linear operators in order to take in. Yeah? So, but the operator is not a subspace. Yeah? So, but what is a subspace? Let's say R is a linear operator bounded between, let us say, with X. Let us forget about Z. Yeah? What is the corresponding subspace? Yeah, of course, the graph of A. Yeah? It consists out of all tuples X, AX. Yeah? X running to X. This is a collection of tuples. Yeah? So this is, in this sense, is the definition of the concept of an operator. Actually, of the graph of an operator, but we forget about the graph. Yeah? So we just write it a little bit sloppy like this. Yeah? And then what is the range? Yeah? What is the range of a subspace? Just for example, yeah? Range of T. Well, what is the range of this guy? Well, also all second entries. Yeah? So it is all Y such that there exists X with the property X, Y is in T. And now you can take all notions you know about operator. Huh? What else? Domain, yeah, domain or first entries. Kernel, yeah? Kernel of A is what? All elements which are mapped to 0. Huh? So kernel of T is all X such that X0 is in T. Now comes, yeah, how looks A minus 1? Again, I'm cheating here, right? Because this is abuse of notation because it is not, it's a graph of the inverse. Huh? Yeah, what happens? Well, we switch elements. Huh? So the T minus 1 is what? Now, well, T minus 1 is all Yx as long as Xy are in T. Huh? And last notion, A times B. Huh? Okay, I make it here. What is the concentration? If you multiply to operate, it's not multiply. Actually, it's later, of course, multiply. But yeah. But it's better to think of first T and then S, right? Okay. Yeah, ST. Yeah. No, of course, you start in T with some XY, and then you want to continue with S. Yeah? So what? Then you need you start with XY in T, then you need a Y in S, which has some map, yeah, which will be mapped via S to something. That's it. Yeah? So it is. Let's say Z, all Z's such that they exist. I make it maybe short, yeah. No, this was wrong. XZ. Such that they exist, maybe, yeah? Such that X goes to Y, let's say, is in T, and then YZ is in S, right? And then we take these two and form our new our new linear relation. Okay. And this is what is happening here. Yeah? So now I can explain it. So EZ Z A Z is this in this language here. Yeah? So it is the EZ. Yeah? I can write maybe I told because now I explained everything. Inverse is explained. Yeah, here this one. Huh? So we take Z A Z. No, sorry, we start here. E Z Z, then continue with Z A Z. So it's a multiplication of these two linear relations, yeah, and it is here. Huh? So this is, and now you see this is identified. You see, yeah, I think I was more correct. Identified, I just write A and not graph of A is again. And then precisely we get, yeah, first E minus 1 and then A. Yeah? So this is, yeah, I removed it. Yeah, this object in general makes no sense. Yeah? But if we start to interpret it in the sense of linear relations, well, then we get this one. So this is a linear relation, and now we do spectral theory for this linear relation. Yeah? Okay. So now, of course, yeah. How is it related? How is this specific linear relation related to our pencil? Yeah. And there are some. Maybe I put this stuff this picture. Yeah, I'm running out of time. So one can show here this was that these two essential spectral coincide. Yeah? It's not so difficult. Under some small assumptions, we don't discuss it. So the message here is the spectrum of the pencil I want to investigate corresponds to the spectrum of the linear relation. But for linear relations, there exist results, yeah, for the essential spectrum. There's some literature, Kost, Wilcox, Narkic. Let us keep. Also, Rostov, Warwick. Especially one of ourselves. And so this we will use. So we take two linear, yeah, this is the old result of Thomas Resisov, Jussi Bär, Peter Jonas, and Abril. And the interesting thing is this one here. So we take two linear relations, and now we consider the P stands for project. They are subspaces, so we are in a Hilbert space, so we can project onto them. Okay, we need closed subspaces. Maybe I should mention this. And then we consider the difference of these two projections. And if this difference is compact, then the essential spectrum coincides. And now you see, suddenly you have some techniques to do something. Yeah? So the first result, let me skip a little bit. Yeah? I don't discuss too long the assumptions. So we have some assumptions on this. This is upper fretworm. Okay, let us forget. Then we look at this object. This is, yeah, we need this guy, and the dagger stands for, here in this case, dagger stands for so-called pseudo-inverse, which sounds, but it is just, yeah, under this condition, your range is closed because you're upper fretworm, and when your range is closed, you can invert on the range. And this is the pseudo-inverse. So, and if this guy here, which is, yeah, a little bit technical, but it is a totally different condition than what was before, just complex difference of A and E. Yeah? And we get that these two pencils have the same essential spectrum. Yeah, and the proof was, as I indicated a little bit, yeah? We go to pencil and we go to linear relations, we use this result, and then we go back to pencil. Yeah? And then there's a second one, maybe, I make it also short. Second way to show essential spectrum. There is a characterization for a point to be in the essential spectrum, which uses approximated sequences. Yeah, they are normed to 1 and go weakly to 0, right? And if you use this, you get somehow different result. Yeah? And again, the result is essential spectrum won't change. Okay, thank you.